Hi, I'm Bob Westervelt. Today, I'm happy to introduce Jenny Hoffman from the physics department, and she'll be telling us how to use a homemade scanning tunneling microscopes. Jenny.
Okay, thanks for the introduction. So I'm going to be talking about imaging topological materials, and I'm going to start with a long introduction to topological materials, and please interrupt and ask lots of questions. But actually, let me start by showing my group. And this is the last time we were all ever together in one place. This was in Maine in February of 2020 when we went on our annual retreat. Every year, we try to give a lot of talks at the American Physical Society March meeting, which is the largest international physics conference in the world. It's over 10,000 participants. It's held somewhere in North America every March. And the everybody who wants to can contribute a 10-minute talk. So there's no cuts on talks. So it's a fantastic opportunity for anybody to have a first experience giving a professional talk. You don't need to do international travel. Occasionally it's in Canada. Usually it's in the United States. So it's a relatively easy travel, and it's a good short talk, and it's a great opportunity to network professionally. So every February, my group has a retreat to somewhere in the New England area, and we spend 3 days doing a sort of boot camp where we rehearse our talks over and over and give each other constructive feedback. So this is the last time we did it. This was like 1 week before the world ended in March 2020. You can see Sam there actually, so she joined us in Maine. So that's the team, but a year and a half out of date. And these are the microscopes. This is the other team. Got the people team and the technical team. And this is the suite of, can you see my mouse when I move my mouse on this? Okay.
Yeah.
This is a suite of materials that we've looked at with a scanning tunneling microscope and a scanning force microscope. Some topological materials, some superconductors, charge density wave material, a quasi one-dimensional material, some beautiful magnetic structured materials. Vanadium dioxide has a metal insulator transition that's 5 orders of magnitude in conductivity, close to room temperature. And here are some more superconductors, including the one that we grew with molecular beam epitaxy in our own system. So that was the team of people and the team of microscopes. How do we make the new materials? Some of them we get from collaborators. We have collaborators all over the world, and that's really fun. But we also grow some of the materials in our own lab. And we do it kind of like Legos. Where if you think about each of these colors of Lego as a different element in the periodic table, we can build up structures one at a time by using this molecular beam epitaxy system. This is a big vacuum chamber, and each of these diagonal ports down here is what's called an effusion cell, and it's basically a hot bucket. And you put an element into each bucket, and then you can change the temperature of that bucket, which changes the rate at which atoms of that element sublime or evaporate out of that bucket. And then you have a substrate somewhere inside the vacuum chamber here, which is face down, and the atoms are flying in a molecular beam from each of these buckets. And so by changing the temperature in the different buckets, you change the relative rate at which the atoms fly and land on your substrate. And so instead of relying on some kind of chemical process in thermodynamic equilibrium, we're actually doing a physical deposition where we can build one layer at a time, even structures that might not occur naturally in nature. And once we have grown that material, we can transfer it through ultra high vacuum and down into our microscope, which is off screen here. And we typically are doing our imaging at 4 Kelvin, very low temperatures, where we can get very high energy resolution on the electron states. So why do we grow and study quantum materials? So you guys are probably interested in a variety of types of physics. And when you were little, you probably saw beautiful pictures of the Milky Way galaxy, so astronomical length scales, and also some beautiful pictures of particle tracks. So this is the fundamental subatomic physics that has a mathematically beautiful language to describe it. But in these types of physics, you observe the world, you discover new phenomena, and then you spend time doing the math to understand the world. Whereas in the type of science that I do, we observe the world. So here are single atoms on the surface of a superconductor called BISCO. And then we try to write down equations to understand what we've observed. But then we can take this additional step, which is based on our understanding of the world, we can design new materials and we can build them. So the difference between the astronomical physics and the subatomic physics is that this is open loop physics, whereas in quantum materials, we're doing closed loop physics. So the kind of discoveries that we're making can actually be fed back to change the world that we live in. So it's kind of the Goldilocks length scale where we can actually impact the world. Okay, so some example quantum materials are topological materials, and these are some pretty pictures that I grabbed off the internet from somewhere, and I'll explain a little more in practice what a topological material is. Superconductors, which can conduct electricity without resistance, and so have a lot of potential applications in energy. And also they expel magnetic fields. And so here is a plate of YBCO, a high temperature superconductor, which is held at liquid nitrogen temperature, and a magnet that's hovering above it because the superconductor is trying to expel the magnetic field. And another kind of quantum material is a so-called heavy fermion material. In this case, typically the atoms have some kind of unpaired f electrons, some kind of spin, net spin at each atom, and then the conduction electrons, the electrons that are traveling waves through the crystal, end up partially canceling the spin around each of these atoms, and this causes a change of the interaction of the traveling wave electrons with the local spins causes a change in the band structure that I'm going to come back to later in this talk. Okay, so I'm going to try to give you a kind of conceptual picture of what a topological insulator is. This is the cartoon picture. This is not the mathematical derivation. So what is a topological insulator? It's kind of like a chocolate bar because it has a conducting surface state and an insulating interior, like this foil wrapped chocolate bar. But if you try to open this chocolate bar, you run into trouble because it's as if the foil reforms around the surface. No matter what you do, the surface remains conducting. No matter how many times you break it, the surface is always going to be conducting. And that's a topological property of the chocolate or the interior of the material. So if you in a topological insulator, in this quantum material, you cannot remove the conducting surface. And so you are left with your ever smaller foil wrapped chocolate bar. So how does this happen? So we have to talk about band structure. And so the first question is, what the heck is band structure? I think some of you have taken Physics 195, maybe not all of you. So let me give a really quick conceptual picture of what band structure is. So as I said before, we build our materials atoms at a time, and we can think of the atoms are like Lego blocks. But now that we put all the Lego blocks together, we put all the atoms together, the electrons are moving through the atoms. So we can think of the electrons are like the marbles in this Lego structure that are moving through the atomic scaffolding that we have created. And so what we want to understand is the relationship between the energy and the momentum of those electrons. That's the band structure. So let's back up to a single atom. In a single atom, we know from chemistry that we have discrete energy levels, 1s, 2s, 2p, etc. And if we put a whole bunch of atoms together in a crystal, then all of those electrons can talk to each other. And now the Pauli exclusion principle comes into play. The Pauli exclusion principle says that that basically says that fermions hate each other. An electron is a fermion, fermions hate each other, they're antisocial. And so fermions cannot coexist in the same state. And so if you put a whole bunch of atoms together that individually all would have had the same energy level, 2s, you put them all together, and now all of those 2s states have to change their energies just a little bit away from each other. So this single state of the single atom has to spread out into a band of states just because all of those electrons can't occupy the same state because they're fermions and they hate each other. So in a single atom, we have spectral lines. In a crystal, we have bands. And this is the energy axis here. And this is just representing the fact that there's a spread of energy associated with each individual state in an individual atom. And then what we really want to know to understand the properties of the material is the relationship between that energy, this axis here, and the momentum of each of those electrons. So within this band, these electrons are all traveling waves in the simplest picture, and they have different momenta. And if we can understand the relationship between the energy and the momenta of those electrons, then we can understand something about the macroscopic properties of that crystal. And a simple thing that we can understand is whether that material should be a metal or an insulator. So if we have a material that has a known filling, a certain number of electrons in the material, those electrons could partially fill a band. And if they partially fill a band, then so here's our parabolic band. This is the simplest kind of band you can have. It's just saying that energy is proportional to momentum squared. So a free electron, energy is proportional to momentum squared, just like a baseball. And in this case, this band is partially filled. The green represents the filled states. And if we wanted to get some electrons going in some direction, in other words, if we wanted to excite a current in this material, we would just have to take some electrons from here and bump them up to an infinitesimally higher energy on the other side, right? Just to get a net number of electrons moving in the positive momentum direction. So it takes a very small and almost infinitesimal amount of energy to get a net momentum in one direction in the case where the band is partially filled. So that's a metal. It's very easy to get the electrons moving. On the other case, if we have a filled band, then in order to get electrons moving, we would have to excite them into the next band up across a finite energy gap. And that takes a lot of energy, and that's what makes an insulator. It's a material where it takes a lot of energy to get electrons moving net in one direction. So just by understanding the band structure of the material and the filling, we can understand whether a material is a metal or an insulator. Okay, now some vocabulary. We call the highest filled state the Fermi level. So if the Fermi level lies within a band, it's a metal. If the Fermi level lies between bands, it's an insulator. So let's kind of zoom in on this band gap here. And again, we're looking at an energy axis here, and let me revert to the language of the individual states of the atoms. Let's suppose we have a p level, and then we have the next orbital out, s level. If we turn on spin orbit coupling, so if we let the magnetic spin of the atom interact with the orbital magnetism of the atom, then we get a splitting of these three degenerate p bands. And just zooming in on a chunk of material here, and considering the energy axis here, and let's say this is an insulator, so the Fermi level sits between this p3 halves band and the next s band up, so it's an insulator. And then outside in the vacuum is also an insulator. So we can think of the vacuum gap of the insulator as being a mega electron volt, the energy to create an electron-positron pair, essentially. But there's some sort of continuity between the gap of the material and the vacuum gap of the insulator. And I'm talking in conceptual terms here. But let's suppose we turn up the spin orbit coupling. How do we turn up the spin orbit coupling? We go to heavier atoms. So an atom like bismuth, the orbital momentum of the electrons is going to be higher because they're farther away from the center of the atom. And so this coupling between their spin and their orbital momentum is going to be higher. So the splitting between these p bands is going to be bigger. And if we make it big enough, if we make it big enough, the p band, the p3 halves band can actually pop above the s band. So we've kind of inverted the order of the bands here. And conceptually, if we've inverted the order of the bands with respect to the topology of the outside world, then something has to happen at the interface between the outside world and the inside world in order to accommodate this band inversion. So how do you go from an inverted band structure to a non-inverted band structure? You have to somehow break the gap. So the gap is what separates the bands. And to go from one band ordering to another, you have to break the gap. What does breaking the gap mean? Breaking the gap means putting states in the gap. If we put states in the gap, the states then cross the Fermi level, and at these boundaries here, this becomes a metal. And so that means that if we were to cut the material in half straight down the middle, we would still have to break the gap to make the interface with the adjacent material or vacuum that has a different band ordering. And so no matter how many times we break this thing, we're always going to have conducting states at the interface. This is a very cartoony conceptual understanding of what's going on. So we have these metallic surface states in this material. And these metallic surface states are topologically protected. They're protected just by the ordering of the bands inside the material. And it turns out they're also spin polarized. And I think I talked too much and too slowly, so I'm not going to explain in detail. I'm just going to ask you to take my word for it that these states are spin polarized. What does that mean? That means that electrons that are traveling this way have a spin up, and electrons that are traveling this way have a spin down. So their spin direction is locked to their momentum direction. So what is that good for? So now we have these conducting surface states that are spin polarized. And one thing that you can imagine this would be good for would be some kind of spintronics material, some kind of material where if you're sending a current one way, you know the spin of that current, and then you could use that spin polarized current to communicate information, to control another magnet, etc. And another thing that people are really excited about using these spin polarized surface states for is topological quantum computing. In particular, if you put these spin polarized surface states adjacent to a superconductor, you can have an unusual form of pairing, which leads to a topologically protected excitation that can store information, store quantum information more robustly than a single spin alone. Okay, so how can we realize these applications? I want to switch gears and talk about a particular material. So far, I've been talking in generalities. So let me just pause and ask if anybody has any questions about topological materials generally.
So at what, like, I don't know if this is even a well-posed question, but at what scale can you like build a topological material? Like, are there restrictions?
It's a super good question.
Yeah.
Yeah. And it is really important, because at some point, if you make this thing too small, so if you shrink this lateral dimension here, then this state is going to start talking to this state. So those two metallic states on either side are going to talk to each other. And when they talk to each other, they're probably going to gap out. And so then you will no longer have topological conducting surface states. Another way of thinking about that is that the topology of the surface is determined by the band ordering of the bulk. So if your bulk is too small, then it doesn't have a well-defined band ordering, and you're therefore not going to have a topological surface state. So in practice, this dimension is often on order a few nanometers, like 3-4 nanometers. So it's definitely at the scale where transistors are useful, right? So we're not really size limited, but technology marches ever forward, and I think the best semiconductor transistor fabrication is in Taiwan now, or Singapore. I'm not sure, somewhere.
TSMC.
Okay, thanks, Bob. And they're approaching this limit, right? Like 5 nanometers, 8 nanometers.
3.
Okay, so we're close. But so far, this length scale is still sort of on order of state of the art, but it would allow for a different kind of computing, potentially with spins as opposed to the charge of the electrons.
The surface of topological insulators are conducting. Are there any that are approaching like low enough transition temperatures that they're like superconducting surfaces?
Yeah, there are some topological superconductors. So we we're interested in trying to make them by proximity effects between samarium hexaboride, which I'm going to talk about as a topological material, and then yttrium hexaboride, which is by itself a superconductor at a few Kelvin. And so potentially by using molecular beam epitaxy to grow one on top of the other, you could have a proximity induced superconductivity in the topological material. And therefore you would have a topological superconductor. What's the maximum TC of a known topological superconductor? I think it's still on the order of a few Kelvin. I don't think we have good proof of higher temperature topological superconductors yet. Okay, so let me switch gears and talk about a particular material, samarium hexaboride. This is a material that's been known for 40 years or so, and has intrigued people because it has this very interesting resistance versus temperature curve, where you lower the temperature and the resistance is increasing. That's what an insulator does. But then at some point, the resistance saturates, meaning at some point, lowering the temperature further doesn't increase the resistivity further. And that's surprising. Most insulators would just continue to increase their resistivity all the way down to the lowest temperature you can measure. So this plateau suggests that something funny, some not well understood physics is going on at the lowest temperatures. And this was mysterious for decades. And then in, I think, 2010, Pierce Coleman at Rutgers proposed that this saturation might be the sign of a conducting surface state. So in other words, the insulating is getting more and more, so the insulating bulk is getting more and more resistive, but at some point that insulating bulk is shorted out by the topological surface state. And this was proven in a really nice experiment by J.P. Paglioni, and actually Samantha worked in his lab, I think, at the University of Maryland a couple of years ago, and did some transport measurements on SMB6 herself, and contributed to the result that the if you take a sample of this material and you thin it down and thin it down and thin it down ever more, you find that this saturating resistance changes in a way that suggests that it is a surface conductivity that's causing this saturation. So this is a demonstration that this material has a conducting surface state, but it doesn't necessarily demonstrate that it's topological. There are other reasons why a material might have a conducting surface state that don't have to do with topology. And so the next question is, how do we show, given that this has a conducting surface state, that it's actually a topological material that has this spin polarized property and that could interact with superconductors in a way to enable quantum computing, et cetera. Oops. So at high temperature, this material has low resistance. It's a metal. It has a conduction band that passes through the Fermi level. It looks like a nice parabola, energy is proportional to momentum squared. And it has a couple of flat bands here that come from the F electrons. They're pretty localized around the individual atoms, so the bands are pretty flat. If we zoom in on that, we see that these F bands have a little bit of dispersion, but this energy scale is milli-electron volts, whereas this energy scale was electron volts. So we're 1,000 times smaller in energy scale here. And we can see that these two flat bands have a little bit of dispersion on a much smaller length scale. And now this parabola, we're so zoomed in that we're just seeing kind of two vertical blue lines here. And now as we go to lower temperatures where the resistivity starts to increase, what happens is that this conduction band starts to interact with those localized F electrons. And when that interaction happens, the conduction band, the blue band here, opens up a gap in the density of states. It hybridizes with those flat bands, and that interaction causes the bands to change shape and open up this gap. The Fermi level lies within this gap, so that means that the bulk is an insulator here. And so then the question is, at the lowest temperature, does this insulator have a, because the blue band crossed the red band, so we've inverted the order of the bands here, does this insulator have a topological surface state that forms to connect these inverted bands at the surface? So our goal is to look for this conducting band at the surface. So our goal is to look for this, and we use scanning tunneling microscopy. I think you did a little bit of pre-work on Monday about scanning tunneling microscopy. Okay, so this is our microscope. It's about 4 centimeters across. We have a very sharp tip that's pointing up here, and our flat samarium hexaboride sample is face down here. We're going to take this tip and scan it back and forth across the sample, and at each position in space, we're going to measure a tunneling current, and that tunneling current tells us about the properties of the electrons in the material. So a brief review of what I think you studied on Monday this week. So we have a tip and a sample. This is actually geometrically upside down, but the same circuit. We apply a voltage to the sample and we measure the current on the tip. When the tip and the sample are at the same voltage, we have states filled up to the Fermi level in the tip. We choose the tip to be a boring metal so that it's got a flat density of states. The sample is the interesting thing that we're looking at. It has some, funky density of states, which is what we're trying to measure here. When we have 0 voltage, the Fermi levels are aligned and there's no net current flowing between the tip and the sample. When we apply a voltage to the sample with respect to the tip, we're changing the Fermi level of one with respect to the other. And now all of these filled states here will find it energetically favorable to move into these empty states here. And the net current tunneling from the filled states into the empty states is proportional to the area of the filled states, which we have designed to be a boring rectangle, and we're just going to divide out, and the area of the empty states available for tunneling into, which is the interesting thing we're trying to measure. So by changing this voltage between tip and sample, we sweep out this area as a function of voltage, and we can take the derivative of that. And when we take the derivative of that area, we're going to get the density of states as a function of every individual energy. It's also proportional to the distance between the tip and the sample, which means we're exquisitely sensitive to vibrations. So like if a spider sneezes next door, we might notice it in our current. We go to extreme lengths to do vibration isolation. And I have had a bunch of really excellent undergraduates working in my lab over time, engineering ever better vibration isolation so that we can take higher signal to noise data. And I still have projects, engineering projects. So if you have friends who are engineers who want to work on engineering projects, we have a lot of work to do always to improve the signal. So with our STM, we take essentially a 3-dimensional data set. We scan in X and Y. We change the voltage, which gives us the energy axis of our density of states. So here are some example data. Here's our density of states as a function of energy. That's when we park the tip at a single location and sweep the energy. Another thing we can do is fix the voltage and just scan the tip back and forth. And so we're collecting a slice in XY, real space, as a function of energy. So we can get a map that looks like this. We can also do a feedback loop where we're keeping the tip at constant distance from the sample and map out the actual geometric contours of the surface. Okay, we're exquisitely sensitive to vibrations. This is when Lisa building was being built. Our lab is way down here. That's Gordon McKay. This is looking out what was then my office window from the front of Jefferson as this was being built. That's the music building, Science Center. So we scan the tip and we can image individual atomic defects on the surface of the sample. This is 5 nanometers. I think I'm running out of time. So yeah, okay, Bob, you're gonna tell me shut up.
Oh no, but wrap it up in a nice way.
Okay. So we can take these maps as a function of energy, and what we see is that the electron waves scatter off the defects. So if an electron wave scatters off a defect, the incoming and the outcoming wave form a standing wave of interference between them, and by measuring the standing wave, we can back out the wave vectors of the initial and final wave function. So this is the crew boathouse where I rowed as an undergraduate. And so suppose that we have a bunch of water outside and we don't know what water is. We want to understand the properties of water. What do you do to understand a substance that you don't know anything about? You perturb it. When you win a crew race, you throw your coxswain in the water. So there's me, the experimentalist, perturbing the water. And what do? You get an interference pattern, some kind of waves on the surface of the water. And by measuring the wavelength versus the velocity of the wave, you can determine something about the properties of the water, like the surface tension. So we do the same thing in our material. We put in defects, and each defect scatters electron waves. And by measuring the wavelength versus the energy of these electron waves, that's how we get the band structure of the material. So because I'm out of time, I'm just going to skip straight through. So actually, that's maybe not useful. Let me skip to the, so this is our samarium hexaboride, and we're looking at how the electrons are scattering off of these individual defects as a function of energy. And the punchline is, by looking at how the wavelength varies with the energy, we can plot wavelength. Inverse wavelength is momentum in quantum mechanics language. And energy is the voltage that we tune with our microscope. So actually, this is our independent variable. We sweep the energy as the tip sample voltage, and then we measure the wavelength, our dependent variable, but we plot it in this energy versus momentum plot, which is a standard way to plot band structure. And our question was really, do we see the surface states here where the parabolic band crosses the F bands? And the answer is yes, we do. And let me just fast forward here. So as a function of energy, we are seeing this wavelength disperse inwards and disperse outwards again, which gives us the shape of the Dirac surface state that would be the signature of a topological material. So that's the punchline in a 30-second nutshell. Okay, that was super fast. So it's time for questions, but I also just want to say that, oops, we have a lot of undergraduates in our group, and I guess 3 of them are sitting here in this Zoom talk right now, but I'm always happy to have more undergraduates talk to me about research.
Well, great. Well, thank you very much. That's really nice. More questions? Wrap things up. What?
Quick question. Like,
Sure.
what is like what makes like the non-abelian statistics non-abelian? Like, what does that mean?
Oh man, that's a question I wasn't prepared for. So when you pair a topological material with a superconductor, so in a typical superconductor, electrons are paired, and the electrons are paired spin up, spin down. In a topological superconductor, the electrons are paired in a way that they have only a single spin. So in this spin, in this type of superconductor in which the electrons have only a single spin, so the pairs act like bosons. So a superconductor, you can think of it as a Bose condensate of paired electrons. So when you pair these electrons, the pair is no longer a fermion. The pair is a boson. It's got an integer spin. And so you have this condensate of bosons. And once you have a condensate, the number is no longer a well-defined quantity. There's an uncertainty principle between the number and the phase, but we can kind of think of the condensed bosons as being like a sea, and we don't worry about how many they are. So if you have an unpaired electron in this sea of condensed bosons in this superconductor, and then you add another, then this pair kind of goes into the sea and goes away. So you can kind of think of each of these electrons in your spin triplet or your spin polarized superconductor. You can think of these electrons as being their own antiparticle. And that when a particle is its own antiparticle, it's called a Majorana fermion. And people are really excited about Majorana fermions for quantum computing purposes, because when you take 2 electrons around each other twice, you get back to the state you started with. If you take them around each other once, you get back to the opposite state. But an anion is something that if you take them around each other, you get to some fractional phase. And furthermore, it depends which order you go around each other. And so it's the fact that the order in which you took these things around each other matters, like the history matters. It's not just where they end up. It's like the order that you did things encodes some lasting information in the system. And that means that if a local blip comes by and flips one of your spins, it can't just flip one of your spins, because the whole information in the system is encoded in its history of whether it ran around this way or whether it went around this way. That was a very vague, non-mathematical description of what's going on. I don't think I have a better answer for you that I can put in a nutshell.
Pretty good. One last question.
I have a question that we discussed earlier this week when we were kind of doing some pre-readings. We talked about a Landau quantization and quasi-particle interference. And kind of the end note of that little chapter that we were reading was that they have never been observed at like the same temperature level. And when there have been measurements made, they kind of resulted in like different results with pretty huge discrepancies.
Yeah.
And we really didn't know why that would be, or how that's still like, how you can like combine the two when they look so different.
Yeah, so that was actually, that was a problem in graphene, where the only material in which both Landau levels and quasi-particle interference had been observed was in graphene. And it turned out that one of those graphene samples was on a conducting substrate, and one of those graphene samples was not on a conducting substrate. And the one that was not on the conducting substrate had been gated by the STM tip itself. And so it was actually exhibiting different physics. And what we ultimately showed, we looked at antimony, which is a topological semi-metal. And in antimony, we were able to observe both the Landau levels and the quasi-particle interference in the same material. And it's a semi-metal, which means it's a pretty good conductor. And so it didn't have this tip gating effect. And we found that they agreed well with each other.
Okay, nice. So that was like a very specific problem, not physics doesn't make any sense.
Right. I mean, at first we thought this physics didn't make any sense. We were really flabbergasted when we found that these two papers didn't agree with each other, but then we were able to find resolution in antimony.
Thank you.
Okay, well, maybe we should wrap things up here, but Jenny,
can I say one more cool thing, please?
Oh, of course.
So here's something that's really cool. So all of this is wave physics, right? We're just talking about electron waves. And all of this band structure, these concepts exist for classical waves as well. In particular, they exist for sound waves. And so a whole other branch of my research group is devoted to making acoustic analogs to these quantum materials. And so we spend a lot of time, we have a whole army of really outstanding undergraduates who are working on acoustic metamaterials. So they make these macroscopic structures that kind of behave like atoms for sound. And in particular, we modeled an array of pillars in hexagonal lattice, just like graphene. And we were able to show a topological transition in this array of pillars by changing the radius of the pillars. And we could make a topological surface state, which corresponds to a sound waveguide. And we could show that if you change the temperature, you're thermally expanding the whole thing. And changing the temperature can then take it through the topological transition where the sound can turn on and off. And so we have speculated about the possibility of building a topological transistor for sound where the output of one sound waveguide, ultrasound waveguide, causes enough heating to move the next one through that topological transition by heating the next one over. So here's just a simulation of how you can turn a set of topological transistors from off to on and build an AND gate here. And this was done by Shivam Saduka, who's a senior undergraduate here now. And we actually kind of simulated how you can build a massive thermal expansion material. This is pouring boiling water on a 3D printed structure, hexagonal lattice here. So this is a lot of fun, how we can kind of simulate the quantum mechanics with sound waves in a macroscopic, tangible way.
Wow.
That's all.
Can I ask one more follow-up question?
Yeah.
Why? It's
Why?
cool. It's really
Yeah,
cool,
no,
but why?
Yeah, no, that's a really good question. Why? I mean, we started it because it was cool, because like, how do you understand quantum mechanics? Nobody can understand it, right? So our attempt was to try to understand it by building something that was macroscopic and tangible. And I think at this point, our argument is that a metamaterial has continuous tunability. So if we build our metamaterial as air cavities in a plastic matrix, then each air cavity acts like an individual atom, and we can continuously tune the size of that air cavity because it's a macroscopic thing. You can make it 3.1 millimeters, 3.2 millimeters, et cetera. So in the periodic table, you have 100 discrete elements, and that's what you're stuck with. But in a metamaterial, it's like you can interpolate, and you can make chemistry that doesn't exist in the periodic table. And then you can think about how could we take the periodic table and make it happen? Maybe we could apply pressure, maybe we could apply magnetic field, but those are really hard experimental regimes to access. So you maybe want to kind of model this in the acoustic world first, and build your experiment in this kind of macroscopic 3D printing, like $100 way, before you go to the $1 million piece of equipment that's going to apply gigapascals of pressure to try to get you into a new regime.
That makes sense. Thanks.
Well, that's wonderful. Well, thank you very much, Jenny. It's exciting stuff, and I particularly like this last one. It's kind of nifty. It's really good.
It's fun.
Okay, great. Well, thanks so much. Next week we have Matteo Metrano will be talking about X-ray scattering, and I've asked him for some good introductory material so we can learn about that in advance. But thanks very much. And
thanks, Bob. Thanks everybody for good questions. Hey, Catherine, are you going to be on campus tomorrow?